All right. Welcome, everybody. This is one of several faculty seminar talks we're doing this fall, actually this year. And I was asked to talk about our Electron Microprobe lab, which is in the beginning of its 10th year of operation. And it seemed like a good time to take a little bit of a retrospective and also think about all the kinds of great things that this has let us do here at Concord University. All right, so this is the lab as it looked back in 2010 in the fall. And the equipment had arrived several months earlier. And my first view of it was actually in the spring, because I actually interviewed for the job here in spring 2010. And it did not look like this. It was not all put together. I walked into a room with a bunch of parts, and there were boxes on the floor and cables strewn about everywhere. And it did actually cross my mind, that's like, if I accept this position, what am I getting myself into? Is this actually going to work? But it's worked, and it's worked very well. And we've come a long way since 2010. The lab actually looks quite a lot different than this. There have been a number of improvements, so we'll look at some of those briefly. So what is this thing? Essentially, it's a specialized type of electron microscope. And like any electron microscope, there's a place to put in your sample. And this is where the electron beam would be. The electron beam was sourced in the top and comes down through some magnetic lenses and eventually hits a sample in there. And then there's various kinds of detectors to measure the signals that come off. And then there needs to be some electronics to control what happens and read those signals and turn them into images and whatnot. So there's some of these other electronics around here, as well as a computer that control and work with those outputs. So the Electron Microprobe is, again, a specialized kind of electron microscope. It can do all of the same kinds of things you'd expect an electron microscope to do. We can take pictures, which is some microscopes, that's their primary purpose. And so we can throw in a wide variety of materials in here and look at them and see their shapes and textures and things like that. But we can go a lot beyond that. Okay. So this instrument also has X-ray detectors and an optical microscope. And those are two key things that make this different than an ordinary electron microscope. So in this case, we have a couple of eyepieces here. This one has eyepieces on it just like an ordinary optical microscope you might have on a bench. You can actually look in there if you wanted. And then mounted around the outside are X-ray detectors. There's one here. This is a cooling tank or a liquid nitrogen tank for another. And it turns out it's those X-ray measurements that lead to us being able to do analytical chemistry. And that's what really the purpose of an electron microprobe is. But you can't just run a lab like this in isolation. There's a whole support network of other things that work with this and to back it up or to prepare things to go in here. So we have developed over the years a whole sample preparation facility. So we can take our own materials, whatever we need, and prep them and so they can go in the instrument and be looked at. Sometimes if it's a rock or mineral fragment, it might require some cutting and grinding and polishing and things like that. Other things, it might be just sprinkling a few little grains of something onto maybe a carbon disc. Most materials that go in here don't conduct electricity very well. And since we're essentially sending an electric current onto a material, if it weren't able to conduct that electric current away, it would build up like a static charge, and then things wouldn't work very well. So we have a coater to actually put film of carbon on the surface to make it conductive. And there's an optical microscope in the lab. Also, sometimes we want to take a look at a sample optically before it goes in. And we do a lot of scans of the samples because we usually use pictures for navigation. in the instruments. We'll often take some kind of picture with the scanner and then load that into the instrument software to help us find our way around. Well, like any other analytical instrument, we also need to be able to have a way of calibrating the system and be able to do quality control checks. So it's like, okay, if I put this in and I try to do an analysis, am I getting good data? Okay. And so we need a whole collection of reference materials of various sorts. Some of them are metals. That's what this illustration is. This is an actual mounted up set of metal samples, and the real size of what you see here is about a 1-inch disc. Okay. And we have several others. I didn't even put all of them on. We have some other mounts too. So there's a whole assortment of materials that are used for testing and setup and calibration and quality control and all of those sorts of things. And no lab like this can exist without that kind of a collection. And so we've put together 200 or 300 materials to do this, so that we can then do a lot of different kinds of applications on the instrument. All right, so this is what the instrument looks like today. I actually took this photograph yesterday, and so towards the end of the talk, there's going to be a little bit of time to come in and visit the lab, and it's more or less going to look just like this. Some of the same, well, actually, those have been moved since yesterday, but most of the things are the same things in the same places. You might notice it looks a little different. The 2010 picture didn't have these computer monitors up here. There's another little box sitting over here. The big liquid nitrogen tank is gone. There are more detectors. There wasn't a detector here before. There's a new detector mounted in the back that wasn't there before. They actually have digital cameras on the eyepieces now. There are a whole bunch of changes and improvements that have happened in the lab over the years. Actually, there's another one. You might see this platform down here underneath. The whole instrument is now sitting on top of a approximately 2-ton slab of steel and plywood that separates it from floor vibrations. Okay. And all of these things have helped make the lab better and more productive than it was when we started. Okay. There's also actually back here, this is a dedicated air conditioner. All of the electronics on an instrument like this can produce a fair bit of heat, and we don't want the temperature in the lab going all over the place. So we have some dedicated climate control. And all of those things help us produce better results. So this slide is a summary of some of the major things that have happened in the lab. Some of those things I pointed to in the photograph a moment ago. And so by fall 2010, everything was put together, tested, ready to go. But we didn't have the sample preparation facility. We didn't have the reference material collection. We didn't have an air conditioner yet. So a whole bunch of things were established so that we could do what we needed to do and have a good environment. Okay. And then one of our first really major upgrades was in 2012 when that old X-ray detector with the big liquid nitrogen tank got replaced by a new modern system. And that, we don't need liquid nitrogen anymore. That's much more convenient. You can turn it on whenever you want. And that also gave us digital imaging. And so our ability to actually collect those pictures is a lot better and a lot more flexible. There are more things we can do with it. We actually use this system extensively. And some people come to use the instrument specifically for this, use that system, that detector. And we added that other optical microscope that was on the side table to the lab a year later. And in 2016, we actually got a whole other instrument. So another university was retiring theirs. They got an email out of the blue and they said, hey, do you want it? And so we figured out a way to acquire that. That's kind of like the story for back here in the original. It was kind of a, hey, do you want this instrument? And amazingly enough, we had people with the foresight to say, yes, nobody's ever done this at an undergrad school before, but we're going to do it. Okay. And so based on that second instrument coming in, we were able to add some additional X-ray detectors, and we have a whole set of spare parts. So if something breaks, there's usually a replacement for it in the closet or the attic, and we can get things back up and running fairly quickly. So that helps also ensure the long lifetime of the laboratory. So we can keep things running for many more years to come. And then like that vibration platform I mentioned, that was just put in over winter break last winter, and we installed in the spring a new system for moving the sample around that can hit targets more reliably. And we're still kind of tweaking and improving that prototype design, keep getting better with that. And we got some new detectors in there that let us look at lighter elements much better than before, and a major new computer system which will process through all of the measurements and output the data a lot faster. And as it says down here, almost all of this has been funded by money from outside the university. And so all of our students and faculty and people who've come to visit have benefited from all of these improvements over the years. And most of it's been funded by grants and a few paying customers who've helped us to buy a few small things over the years. Okay. All right, so what can we do with it? All right, so I mentioned pictures earlier. That's a pretty basic capability of most electron microscopes. And so yes, we can do imaging with the electron beam. About the lowest magnification we can get to is about 100 times magnified. Which overlaps your average optical microscope. And we can fairly routinely get up to about 10,000 times magnified. It can go higher, but it takes a bit more fussing and tweaking to get good results at higher magnifications. And this, of course, is way, way higher than any visible light or optical microscope can achieve. And again, it's an analytical instrument. We're trying to measure the composition of materials, and so we can actually work with most things on the periodic table, except for the very lightest elements. Okay. And that's done through using the X-ray detectors. Okay. And I have a few examples of these, some of these pictures coming up. All right, so we can also measure individual spots. So we can say, okay, instead of, let's say, scanning the electron beam around to see what things look like over an area, like what is this made of right here? Okay, and that can go down to about almost 1 micron. And if you want to have a comparison, think about the hair on your head. The average human hair is probably on the order of like 50 to 80 microns. So if we say 50, where this is at least 10 times to 50 times smaller than the diameter of the hair on your head. It's pretty small. Okay. And we get really great analytical precision on our measurements, and not just things that are abundant, but also things that are there down in trace quantities. Fairly routinely, we can go down to about 100 parts per million. That's like 1 atom out of a million atoms, 100 atoms out of a million atoms. And we can go lower than that for special cases, but again, pushing the limits requires a bit more work and more effort than routine things. Okay. So if you're going to put a sample in, it usually goes into a holder like this. So the ones we use most often I've put up here. So this one we can put in 5 samples, or 5 mounts, maybe with multiple samples in a given mount sometimes. And these are those 1-inch discs I mentioned earlier. We could also put a couple of those discs into this other holder. This one is really meant for sliding in a thin slice of rock or other material on a piece of glass. We call those thin sections, and we use those quite a lot. That's something that's very common for geological work, but not necessarily common for other kinds of disciplines and their analyses. All right, so we put this in. A common material that we'll put in is volcanic ash, and we'll often use the electron imaging to find our way around and figure out what targets we want to pick for more detailed work. In this particular case, we have some fragments of ash that are mostly glass, like these. This is sort of like shattered pumice, and you can see where some of the bubbles would be. Think of like volcanic foam that blew itself apart. Some of these over here have crystals in them. So there's a crystal here of some kind of mineral, the little thin film of volcanic glass on the outside. This is a different mineral, we can tell because it's a different brightness. And here's another mineral that's a little bit darker. Sometimes we can even see variations in the chemistry, because that's what this imaging is reflecting within things. So like this crystal, this actually has a slightly darker rim on it. This piece of volcanic glass has a little slightly different colored rim on it. These have actually absorbed a little bit of water around the edges. And we can actually see those subtle compositional differences in the backscatter imaging. It doesn't tell us what the exact chemistry is, but we can get a general sense of, okay, does it have more heavier elements in it, maybe like iron rich, which might show up bright, or it has more lighter elements in it, like actually the epoxy glue that's in between here that you can't see. That's mostly like carbon and oxygen, and it shows up really dark by comparison. All right, so if we wanted just a quick look at chemistry, we're going to use that new detector that I mentioned was mounted in the back, and that was added in 2012. That was our energy dispersive X-ray detector. It gets an entire spectrum at once. Okay. So X-rays are just part of the bigger electromagnetic spectrum, and we've got visible light, and we've got radio waves, and infrared, and ultraviolet, and all of that. And X-rays are over there next to ultraviolet, but going towards higher energy. It turns out that X-rays can provide information that's characteristic of the elements that are in a material. Different elements can give off different X-rays when you put an electron beam onto them. And so this spectrum, we have iron in here and calcium, and there's larger signals for those, so there's quite a lot of that. There's a little tiny blip here for manganese and a little one for chromium. So those are there only in very small amounts. Okay. And then over here we have things like silicon and aluminum, magnesium, oxygen is this big one here. And so very quickly we could put in a material and see, oh, okay, basically what's in it and which things are abundant and which things are not. And this could be useful also for figuring out, well, okay, what is this material I'm looking at? So we could have an introductory course of, let's say, Geology 101 students come in and put something in from their lab and say, oh, which mineral is this? Okay. If we want to get more quantitative, then we need to spend a bit more time, have an analytical routine set up with specific elements and calibrated using specific materials. And again, this is another example using volcanic ash. We do quite a lot of this. And some people will send us their samples to have us analyze them for them and figure out what eruption it came from. These are individual data points in rows and an average, and then it compares, oh, this one came from the big eruption that made Crater Lake National Park a thing. Okay. This is some of our early data. Again, we've improved the lab over the years, and we can do things in a lot more detail, more precision now. This one has a bunch of additional elements on it. So there's some trace elements in here, but we also have some abundant elements, so like 38% SiO2, 10% aluminum oxide component. Those are fairly abundant. But then we have things down here, 0.005 on chlorine. That would be equivalent to 50 parts per million, or 50 atoms out of a million atoms. And for some of these, we can see our precision is really good. For major elements, we can fairly readily achieve a relative precision of about 1% or less relative. So 38 plus or minus 0.2, that's a pretty tight measurement. It's a little harder to get that level of precision at trace element level, so you'll see the percentages and the variation are higher. But still, we can get out to 3 decimal places on a lot of things pretty readily. Okay. It turns out we can combine some of that X-ray analysis and the imaging together. And then we can say, okay, is this science or is this art? I threw in a few particularly stunning examples, run through a few of these. This one, actually the target was a piece of art. So I had one of the faculty in Concord's art department provided me with some pieces of pottery, like a nice little cup with a glaze on it that they fired in a kiln. And this is that colored glaze on the outside. And it turns out a lot of ceramic glazes are actually made of ground up minerals. And well, if you've got melted minerals, that sounds kind of like magma or lava. And it turns out a lot of ceramic glazes, you could think of them almost like experimental lava, but a thin layer on a piece of pottery. And if you cool them at the right rate, they can grow crystals just like a real lava flow could. And that's what we're actually seeing in this image. These are actually feldspar crystals, and geologists would actually recognize these because we see crystals that grew with these same kind of branching patterns in actual lava flows. These crystals down here are actually magnetite or iron oxide. And there's a lot more detail in here. We can zoom in on this. And you can see there's a lot of very fine, detailed textures in here. These things grew like Christmas trees, looking kind of. We also actually have images. Sometimes we'll put in samples from rocks that were melted during earthquakes from the friction. And sometimes they'll grow little crosses of magnetite similar to this. So this can tell us something about not just what the chemistry is, but also the shapes and textures of maybe crystals that might form. And those shapes and textures might tell us something about the conditions, like the cooling rate or the temperature thing that some of these things relate to. A couple other examples. Here's another one. This is the glaze. This is the body of the pottery with actually chunks of quartz, and the rest of it is clay in between. And again, this one has some little crystals in it. And there's even apparently some kind of chemical reaction that happened between the glaze and the bulk of the pot, because there's some different things that showed up right along that interface that don't show up elsewhere. This one I like. Doesn't that kind of look like maybe if you're at a lake or a swimming pool and the light was filtering down through the water and you looked at how the pattern of the light on the bottom of the pool looked from playing through the waves? It looks a lot like this, except this is chemistry. This is actually differences in the amount of calcium. There's more calcium, less calcium, but it actually looks kind of like waves. And then we have a few others, a couple others I threw in. These are from rock samples that our students have put on the microprobe that turned out with some interesting images. And really what this is doing is it's a combination of the different minerals. And so we have this over here. This is mica. The red is actually little veins with iron oxide in there. This darker blue, this is quartz. And so it's a combination of the natural mineral textures in the rock and then the chemistry, which we present with different colors. So, and you can choose the colors. In this case, we made silicon blue. And so there's a little bit of art to this. You can pick the colors and find something that works together well, that highlights the features of the rock, and perhaps you could argue comes out with a piece of art. And this is just another one. This is another rock that had a fracture in it, where little tiny broken pieces were kind of floating in that fracture. Iron oxide came in later and filled it in. That's what is shown in red. It's rich in iron. And actually, later, the rock cracked again in almost the same place. Okay. All right. So this slide, I don't expect you to be able to see this in detail, but the idea here is that there are a whole lot of different kinds of applications. We mostly do geological things here, but there are a lot of other things people can do with this. It could be used in archaeology and biology and pharmaceuticals. I mean, I know a place where they have a dental school that has an electron microprobe so they can look at teeth. we might use it in things like energy. People will look at like the ash that comes out of a coal-fired power plant. We might use it in forensics to try to characterize evidence. Manufacturing, quality control. I know somebody whose part of their job is involved taking the catalytic converter out of an automobile, which is part of the emissions control, and they find that, okay, their product is failing prematurely and people are having to replace the catalytic converter in their car too often. Why? Why is our product failing? So they literally will slice up pieces of that catalytic converter out of that used one out of somebody's car and put it on an electron microprobe to see, well, what is going on there? Okay. Some labs get into things related to like solar power and computer chip manufacturing and things related to that. Some, they basically pay the bills by using the electron microprobe to measure the thickness of a thin layer of material that's deposited on some kind of substrate, which helps them test manufacturing processes that are relevant to things like solar cells. Okay. All right, so what do we get out of it? So the instrument supports a whole variety of courses. We use this for our introductory geology and chemistry courses and a whole series of other courses in especially the geology major on up from that. We have students who do independent research projects that use the instrument all the time. And of course we have faculty who do research projects using the instrument, providing important data to answer all kinds of research questions. And of course, having a capability like that is useful for bringing people here, and so it enables them to do things they might not be able to do elsewhere. And I mentioned earlier that it's really a unique kind of thing. Concord being one of the first places to ever do this with mostly undergraduate students. This instrument is the only place in West Virginia with these capabilities. And as far as I know, we're still the only primarily undergraduate university in North America with the capability of doing this sort of work. Usually you have to go to like the big schools, and even some of them don't have this kind of instrumentation. So that's a draw. People can come here and do things that maybe they wouldn't do other places. Almost nobody is probably taking Geology 101 labs and putting them on an electron microprobe routinely, but we do that here. We bring in the community on occasion. Sometimes there's an open house. We've had like the local Cub Scouts in here in the lab. And of course, having this kind of instrumentation, which enables research, that also enables people to be more competitive for acquiring grants that can support a whole lot of other things. And we could bring in contracts. People will pay us to analyze their samples. And we wouldn't be able to do those things in the same way otherwise. And of course, this also builds in networks of collaboration. We have research faculty, research students working on projects with people from other universities. And sometimes they'll come here. Sometimes it's a project where maybe somebody in Montana and somebody here at Concord are collaborating together on something from the Rocky Mountains, and we can support that research. So some pictures. This is a Geology 101 lab from a few semesters back that was in the laboratory, and we were doing igneous rocks, and there's a photograph here of a piece of rock that's actually in the instrument, and this image you could see matches over here. This is what we were looking at. We figured out, okay, this was a granite, and it has feldspar and mica, actually two kinds of feldspar, plagioclase, alkali feldspar, and let's see, I think this is more plagioclase down here. And somewhere else in the rock we probably ran into some quartz. And so they could characterize the crystals in there, what minerals there were, and learn more about the rock than they could just by picking up a hand sample. Okay. We have students doing research projects, and these are a couple of our alumni actually. And there are all kinds of benefits from this sort of thing. We've actually had at least a couple of students whose experience in the lab doing a geology research project helped them get their job after they graduate, and others just helped them get into graduate school, compete for those sorts of positions. We have a student right now, not one of these two, who now works at the National Institute of Standards and Technology, and she was actually a student employee in the Microprobe lab a few years ago. Of course, not all research spends all of its time in the laboratory. Sometimes people go out in the field and do research elsewhere, and then maybe they need to bring samples back. And so the analytical capabilities back here at the university can help support research projects where students go out and get experiences in other places. And so these are some students who were working on some projects involving Ice Age lakes in Oregon, and we were using volcanic ash, like this one right here, as time control, age control for the lake history. And well, to figure out what eruption and what age that is, we need the electron microprobe. Might also go up and look at volcanoes, maybe closer to source where there's a lot more ash and a lot more pumice piled up. And again, bring samples back. It's like, how do we figure out the history of this volcano? How many eruptions, when did they happen? How do I know if this stuff over here is the same as that stuff over there? And so we've had a number of students working on volcano-related projects. Actually a couple summers ago, I had people up on that ridge right there. Samples from that locality have been brought back to the laboratory and analyzed. And students have done research presentations at meetings and conferences based on those samples. There's another one looking at ancient earthquakes, actually out in some of the same lakes. Again, when did these earthquakes happen? Well, we need to know the ages of the sediment layers that the faulting cut through. And in this case, we're again using volcanic ash. And so we might take a sample, it goes through a preparation process, goes into the instrument, maybe we take some pictures, and we might get some chemistry. That's a common thing. We also have research that's done on frictional melting that I mentioned earlier. This is one of these thin rock slices on a piece of glass, viewed using a visible light microscope, but with polarized light, which is why it has these different colors showing up. And this is of what used to be glass from what was melted and then solidified when an earthquake moved. And I don't know what, from this particular one, either maybe it moved that way, maybe it moved that way, but you can imagine two surfaces rubbing against each other deep underground during an earthquake, making this vein. And so we have active research projects, and some of this research, this one in particular, is actually integrated into some of the upper level courses. So we have students with a lot of hands-on experience learning how to do this and what it means. And so we'll get some pictures as the student. These are actually taken by some of the students trying to understand what their rock was and what the features in there meant. Sometimes we'll run into some rare and unusual minerals. This is one of these samples where we found a fairly unusual mineral that has quite a bit of, like, really obvious, that's thorium, by the way. And that kind of thing is interesting. Thorium's radioactive, and geologists like to use radioactivity as a clock to date things. It's like, oh, does this mean we now have a way of figuring out when this earthquake happened? Maybe. Okay. And sometimes we'll do samples for other people. So this is a list of a number of different universities that have either sent us samples or had people come visit us. Northern Arizona University, for example, sent a PhD student all the way here from Arizona a few years ago to use our laboratory. We've had faculty from College of William and Mary and Slippery Rock here several times. Some of these other ones, Texas A&M, send us samples from archaeological sites, for example. Okay. All right, this is the last slide. I wanted to wrap up with something very, very recent. I mentioned earlier that having an instrument like this opens up a ton of opportunities and for things that students can do, faculty can do. And this is one of the most recent examples. This just came out last month in September. A 1, 2, 3, 4, 5, 6, 7 different institution collaborative proposal with Concord University part of it just was awarded $1.6 million. And Concord would not be part of this if it weren't for the Electron Microprobe Lab. All right. Are there any questions?
Tell us how many samples you might need to run, how many data points to determine a kind of eruption from the blast shards.
So the question for those on the video is how much analytical work, like how many data points might we need to be able to actually fingerprint a volcanic eruption? Actually, it's probably about a dozen. It's not terribly many. It depends on the chemistry. Sometimes the chemistry is very, very uniform, very tight. And other eruptions where it's sort of like different magmas were kind of blending together as the volcano was coughing this stuff out of the ground. Things with more complicated chemistries take a bit more work to describe thoroughly. So, but yeah, an hour or two on the instrument. That's about all it takes.
Tell us how people find these ash beds.
Well, some of them are easy. Some of them you can see them. Some of them are, like the photo with the student standing in front of, I don't know, that was 50 feet of, actually it was there at least 50 feet of stuff there. And sometimes there's big pumice, you can see it. Sometimes it's just a thin little wisp that was laid down in a lake, and we might have pulled it out as part of a core sample from the bottom of that lake. Sometimes you can't see it. So there are methods now where people can extract trace amounts of volcanic ash that you can't see out of mud or out of, let's say, a peat bog, and be able to figure out even what eruption it came from. And usually that involves some form of separation of particle sizes. So if it's like out of lake mud, we might want to get rid of the really, really fine clay out of it because the volcanic ash might be a little bit bigger. And then we might be able to also run it through separation by density. So we can essentially put a heavy liquid solution and essentially float the volcanic ash particles and sink other things that we don't really care about, and then concentrate it enough where you can see if it's there. Of course, you need to put it on the microscope to even be able to tell if there's anything there. People are doing this at huge distances. Now we have, there's an eruption, for example, from Glacier Peak volcano in the Cascades in Washington State that's now known to be in peat bogs in various places across Europe. And nobody can see the stuff digging into those peat bogs. But if you go through and chemically analyze it on the Electron Microprobe, tiny little traces, sometimes they only have like 4 particles, and that's all they get. And so you really need something that has a microscopic analytical capability to even work on such things.
Any more questions? All right, let's thank our speaker there.
All right. Thank you. All right. So I had intended for this to run a little bit short. We have a little bit of time left in the hour, and you're all welcome to wander across the hall and visit the lab. So welcome to the Electron Microprobe Lab. And this over here is the main part of the instrument, or most of the hard work or most of the business happens. The samples go in through the bottom front here, and we can put in a wide variety of materials. A lot of them are geological, but they could be other things. This is a small piece of material. We have, actually, there's 3 little pieces in there. This one actually is a piece of a butterfly wing. We can look at biological things too. Sometimes it takes a little bit of preparation. Something this size is too big, so we might need to slice it up and put a small piece in. And so that sort of thing would go into some kind of sample holder that might look like this. And this takes 5 different pieces, and that would go in through the front here. This opens up, comes out like a drawer. You set the sample in and then put it back into the instrument. So it's an electron microscope, so of course we need to have an electron beam. And that is generated up here at the top. And then that comes down through the interior of the instrument to a sample that's probably about this high, but back in the center. And when we're doing analytical work, we need to make sure that the sample is at the right height for these X-ray detectors here to work properly. And so we have an optical microscope, and this one has the eyepiece on it. You could actually look in there yourself if you were here in the lab. This one has a digital camera on it, which feeds over to some computer monitors over here, which means we could also send it out to people who aren't in the lab. Somebody could actually access some of this remotely. So we put in our sample, and then what are we going to do? So oftentimes the first thing is some kind of imaging. And so I have here some volcanic ash in there, and we can zoom in and zoom out. So I could adjust the magnification, for example, get a closer look, a farther look. We can actually go up even a whole lot more in magnification if we want. That is about 2,000 times magnified there right now. And we can save those images if we need them. Okay. We can also, there's various types of software in here, some for analytical, some for imaging. One of the things we do quite a bit is combine sort of the X-ray sensor with imaging, and let me set this going. And that's a live slow scan going right now. It's incrementally working its way down. And actually here we can see why it's called a scanning electron microscope, because literally it takes a beam of electrons and draws it across the sample. And this is synchronized, so what we see here actually reflects the real progress inside the instrument. So literally it's taking an electron beam and drawing it across, and then stepping down just a little bit more and drawing it across again, and then feeding the results out of the various sensors into here, and we can see the image. So this is just showing an electron image, and we can also add to that chemistry. So there's a little periodic table in here, and I can turn on a couple of elements, for example, and it'll take the software sometimes a moment to catch up. Oh, I know, I have the sample lowered right now, way below where the X-ray detector can see anything. Maybe I need to do that differently. Let's, it works for the Ecton. I'm gonna need to bring this up. All right, I'm gonna let the computer drive, and it's going to move to a different position and actually raise the sample up to where the X-ray detector could actually see it. And let's stop that. And I need to adjust the focus. It's like any other microscope. You need to be able to have focusing, otherwise you get blurry pictures. Let's see, 6. Okay, I need a little more brightness. All right, we're not focused yet. It's getting better. There we go. Much better. All right, I'm going to zoom out a little bit. Okay, so we're on a different sample right now. And I'm going to go back to where I was before. And let's try that again. All right, now we have the colors. So let me just turn it back to the electron image by itself. Again, we can see it progressing, scanning, bringing in some detail here. And I could turn on, let's say, carbon, which maybe we don't want to be blue. Yeah, maybe I'll make that red. And in this case, the red is actually in between. We're seeing essentially the carbon in the glue, the epoxy that's was used to mount and prepare these tiny little fragments. What are those things? Well, they're volcanic ash, and they have some silica in them. So if I turn on showing silicon, now they're highlighted blue because I set silicon to be blue. There's also aluminum in there. I could turn that on. We can see that they have aluminum, and one could do this for any number of different kinds of materials. And so this is used a lot for trying to figure out what something is, to explore around, and maybe pick targets for more detailed work that we might do later. And for that sort of thing, we might have collected some point data, and afterwards we can output results. All right, so in addition to doing the X-ray imaging and electron imaging together, we can also do point analyses, and that uses some different software. And I can just take an example. We'll have collected some data on some reference materials that are used to set up and calibrate the instrument, and then maybe some unknown sample we're trying to figure out what it is. And after we've collected all of that information, the software can process the results, and usually it takes a couple of minutes. And right now it's going through and loading a whole bunch of the raw data into the system, and then it'll take a moment to crunch through it, and then it'll output the results. There we go. So some of it just showed up here. It's also in the table here. And there's a whole table of different elements and how much of each one there is. And so we have like this one has quite a lot of silicon, quite a lot of aluminum, not very much magnesium. And so we can use that for material identification. Sometimes for certain geological processes, for example, the chemistry tells you something about what happened. Sometimes it might be something about the temperature, or in this particular case, this is some volcanic material, and so actually volcanic ash, and so it might be able to tell us, like, well, which volcano did this come from? Maybe we find some little bit of volcanic ash, and it's like, okay, yeah, where did it come from? It's like, okay, there's a whole bunch of volcanoes over there. Which one? Which eruption? When? And we can answer questions like that sometimes through chemistry.